Buen día a todos. Muchas gracias por su interés y participación en el ciclo de seminarios de la Sociedad Argentina de Espectrometría de Masas, CERUTI, parte del comité organizador de este ciclo de 6 seminarios virtuales, gratuitos, y que hemos organizado en diversas temáticas del campo de la espectrometría de masas. Antes de dar inicio a la presentación de nuestro disertante del día de hoy, invito al doctor Ricardo Fulán, presidente de la Sociedad Argentina de Espectrometría de Masas, a brindarnos, por favor, unas palabras.
Gracias, Soledad. Bueno, buen día a todos. Muchas gracias por conectarse a este comienzo de estas primeras charlas. Bueno, simplemente quería introducir esta serie de charlas que Soledad está organizando este año, que marcan un reinicio del contacto en esta salida lenta de la pandemia de la sociedad con los socios. Soledad está organizando una excelente serie de charlas de este tipo que hoy comenzamos y creemos que servirán como nexo hacia la presencialidad del próximo CAEM que será, si Dios quiere, el año que viene y las condiciones sanitarias lo permiten. Agradecemos a los 6 investigadores que han mostrado su buena predisposición para participar en este ciclo de seminarios y esperamos que el esfuerzo que está poniendo Soledad en la organización de este ciclo sea aprovechado por ustedes, seguramente, ya que hay una variedad de contenidos y de expositores muy interesantes. Así que sin más, agradezco, Soledad, por la organización de esta serie, agradezco a los diferentes expositores, en particular al profesor Michael Sulyok, que es quien nos visita hoy, y bueno, arranquemos y esperemos que todos podamos aprovechar en la medida de lo que se puede hacer con este ciclo de seminarios. Muchas gracias, Soledad.
Muchísimas gracias, Ricardo. Bueno, con la atención de todos y considerando que el idioma de la presentación y de nuestro disertante, el resto del seminario lo vamos a brindar en inglés. Al final de la charla vamos a tener un espacio para las consultas y preguntas que nos pueden ir dejando en el canal de YouTube y también en el Zoom. Gracias, Ricardo. Bien, vamos a dar inicio entonces a la presentación de Michael. Good morning, ladies and gentlemen. On behalf of the Argentine Society for Mass Spectrometry, it's a great pleasure to introduce to our speaker today, Dr. Michael Sulyok, from the Institute of Bioanalytics and Agrometabolomics Department IFA-TUL at the University of Natural Resources and Life Sciences in Vienna, Austria. Dr. Sulyok is going to talk to us about his research in the field of mass spectrometry related to the validation of multi-toxin methods. Our speaker is performing cutting-edge scientific research and developing advanced methods in the field of bioanalytical chemistry. In this sense, Dr. Sulyok is a senior researcher of the Mycotoxin research group focusing on targeted LC-MS method for the simultaneous quantification of hundreds of mycotoxins and other contaminants in food samples. He is a very prestigious researcher who has published 300 scientific articles and other important contributions. Ladies and gentlemen, please join me in welcoming Dr. Michael Sulyok.
Just a moment. So good morning also from my side, and thank you very much for this kind introduction. I will just switch on the laser pointer. Can you see my presentation? Sorry, that
Yes, I can
Okay.
see you and I can hear very well. Thank you.
Okay,
Mike.
that's great. So, as you will see, the term multi-toxin in my title is slightly imprecise, since our institute is focusing a lot on mycotoxins. Sorry, obviously it doesn't work. Okay. It's focusing on mycotoxins, and those substances are, per definition, toxic secondary metabolites produced by molds, so different species from Fusarium, Aspergillus, Penicillium, also Alternaria, and that are proven to be toxic to vertebrates. And since they are toxic, there have been maximum levels established for those compounds, ranging from some 50 nanogram per kilogram to 4 milligram per kilogram in different food commodities. And even this limited set of mycotoxins addressed by regulatory limit is already a chemically very diverse set. So you have compounds like deoxynivalenol, which are quantitatively soluble in water. On the other hand, you have cerealone, which is insoluble in water. You have acidic compounds like fumonisins and citrinine, and you also have alkaline compounds like the ergot alkaloids. And actually, this chemical diversity of the analytes, together with this wide range of relevant concentrations, the different food commodities that should be analyzed, and the fact that authorities like the European Food Safety Agency is interested in more and more compounds, has led to evolution of methods. So in the recent years, there's a clear trend towards LC-MS-based methods, multi-target methods, trying to squeeze in as many of these compounds as possible with minimal or even no cleanup. And this evolution of methods is very well reflected by the work in our institute. So in 2005, my colleague Franz Bertila, he came up with a method for 9 fusarium toxins, including a cleanup step with the QDAP 2000. And he obtained LOT for deoxynivalenol for 65 picograms on column. Then, with the availability of the next generation of instrument, the QDAP 4000, we were able to skip this cleanup step, to broaden the method to 39 mycotoxins. And we obtained a lower LOT for deoxynivalenol of 10 picograms on column. And over the time, with further options in the data acquisition, so for example, the time-scheduled MRM mode, we have continuously expanded the method. And later in 2010, when we acquired the even next generation QDAP 5500, we obtained another leap in sensitivity to 0.3 picogram deoxynivalenol. And that's the instrument that we are still using in connection with, I would say, very conventional chromatography. So you see that's a very long column with 5 micrometer particles and a flow rate of 1 milliliter per minute. I'm just explaining this in a minute why we choose this. The method is run in the scheduled multiple reaction monitoring mode. It comprises at the moment 900 mostly fungal metabolites, and it works with 2 separate injections, one for the positive and one for the negative mode. So the method works with a simple extraction step with acidified citronitrile water mixture, and we have found this mixture to be the best compromise for accommodating both very apolar, polar, acidic, and alkaline compounds. We dilute this extract, and then we directly inject 5 microliters of this diluted raw extract. So we, of course, tried to implement some unspecific cleanup like catchers, which is very well known from pesticide analysis, but we did not sort of come to the conclusion that this really improves the situation, so that's why we omitted. And we really inject raw extract. And of course, working with such dirty samples, poses the need to have your system to be as robust as possible. And that's actually the reason why we stick to the ancient chromatography with a very large column with 5 micrometer particles, because this type of column is able to cope with a dirty sample. So this first Gemini column, which we bought together with the instrument, we was retired just last year after 200,000 injections, which is quite a pro for using that type of column. And the other aspect of using or of analyzing diluted raw extracts are matrix effects. Since all of you are mass spectrometry specialists, you probably all heard of that term. But since some of you might be involved rather in structural elucidation than in hardcore quantitative analysis, I want to explain their impact on quantitation on the next slide. So that's a typical situation you would encounter. So if you prepare a calibration prepared in neat solvent, you get a perfectly nice calibration line down to 0.05 microgram per kilogram. But when you spike a walnut sample at the same nominal concentration, you will probably find, okay, the peak area is only less than 50% of what you would expect. And if you have never heard of matrix effect, what you would do now is to tell your PhD student, okay, obviously extraction has not worked, and please try several other solvent mixture to improve extraction efficiency. And depending on the ability of the student to suffer, he will come sooner or later back to you and admit that he has failed. And that's because he has fought the wrong enemy. Because if you construct the calibration in blank extract instead of neat solvent, you will notice that the recovery of the spiked sample was only apparently lower than 50%, but in reality something like a healthy 90%. And it's actually this difference in the slopes of the calibration function between a neat solvent standard and a standard prepared in blank extracts that's considered as matrix effects. And the gold standard for official control analysis for mycotoxins is the use of carbon-13 labeled internal standards, which are available for all the compounds addressed by regulatory limits. But this is out of the focus of this presentation, since we are dealing with several hundred compounds for which those standards are not available. So what's usually done in practice is that the matrix match calibration is really performed physically. So the serial dilution is prepared in blank extracts. But for our purposes, that involves some practical issues. First of all, it's very difficult for some analyte matrix combination to come up with samples that are really blank. So until now, I found no maize sample that was completely free of deoxynivalenol or formonicins or pulvericin. And the other issue is that in our daily business, we are analyzing a lot of different samples from different matrices, and we would have to fill the auto sampler with a lot of different matrix match standards, and would hardly have any free slots for our samples. So that's why in our workflow, we rely on external calibration in solvent. And this leaves another question: how do we deal with matrix effects, and especially whether or not we consider them to contribute to the recovery of the method? And that's a point which was already almost 20 years ago considered by the IOPAC. So they differentiate between apparent recovery and recovery. And apparent recovery for them, according to them, is an observed value derived from an analytical procedure by means of a calibration graph divided by the reference value. So it's really deriving from a measurement process. And of course, matrix effects, as they are involved in the measurements, contribute to apparent recovery. In contrast, according to IOPAC, the recovery is simply the yield of a pre-concentration or extraction stage. So for recovery, according to IUPAC, these matrix effects do not contribute. And although these matrix effects are known to be sort of the Achilles heel of quantitative analysis, general guidelines in general in that aspect means non-MS specific do not address them. For example, this very well-known Commission recommendation on the performance of analytical methods, they do not even mention matrix effects. They just state that the recovery should be in a certain range. And now that's the crucial question is, what type of recovery do they address? Is it only the recovery of the extraction, or is it the apparent recovery? And that's not easy to answer, because if you consult other guidelines, you will see that both types of definitions are available. So for example, in the Santé guide, they consider recovery as the proportion of analyte remaining at the point of final determination. Or even, maybe even more clear, the proportion of the amount of analyte which is extracted and just presented for measurement. So they decouple this recovery from the measurement process. In contrast, the other two definitions I found is that the recovery is the fraction of percentage of the analyte that's recovered when the test sample is analyzed, which clearly is equivalent to the apparent recovery. And you might not think, okay, well, that's maybe an analytical subtlety. Why should we bother? The problem is, as I said on the slide before, is that there are certain performance criteria. So, for example, it's the most common one, 70 to 120%, or sometimes even more strict, 80 to 100%, to which a method should comply. And it can make quite a difference if it's not the recovery of the extraction or the apparent recovery. To outline this, I'll just show you on the next slide the results that we have gained during method validation for over 500 analytes, and we have validated them in 2 grain matrices, wheat maize, 3 nut matrices, almond, walnuts, pistachios, and 2 types of dried fruits, grapes, and figs. And what you can see here are the histograms, which shows the fraction of the investigated analytes for which the apparent recovery is within a certain range. So the green bars, the 2 green ones here, they cover the target range of 70 to 120%. And as you can see, that depending on the matrix, it's only 48 to 83% of all analytes are in those target range. And especially walnuts proved to be very tricky. So a lot of the apparent recoveries were below 70%. The situation looks much better, however, when you regard just the recovery of the extraction step. So you see almost only the green bars. So it's 84 to 93% of all analytes that are in the acceptable range. So, and there's now the question, okay, if I do matrix matching and my recovery is then for most of the analytes in the desired range, so for example, aflatoxin in walnuts, my recovery of extraction is 99%. Okay, there is some matrix effect, but I compensate it with matrix matching. Am I on the safe side, and can I just use this method? So in other words, are there any acceptance criteria for matrix effect? So would it be okay to work with signal suppression by more than a factor of 2? Well, there's hardly any advice in the guidelines. So the Santé documents, they come up with a 20% criterion, but this means only that if the difference between your standard prepared in blank extracts and the neat solvent-based standard is less than 20%, less than 20 relative percent, you are free to ignore any matrix matching. But what's not clear is if Santé would accept a reduction of the analytical signal by, let's say, a factor of 5 or even 10, as long as you properly compensate it by matrix matching. What they say is that the recovery, and these aspects, again, it's the recovery of the extraction that's considered, should be in the range of 70 to 120% with a repeatability of 20%. And what I found interesting, they add, exceptionally, where the recovery is low but consistent, and the basis for it is well established, a mean recovery below 70% might be acceptable. And I wonder whether there could be any analogy to matrix matching. So even if your signal is decreased by, let's say, a factor of 5, it could still be, you could still perform quantitative analysis as long as you're sure that the signal suppression is always a factor of 5, which means there's no difference between different individual samples of belonging to the same matrix. So it's a question of repeatability. And again, if you consult different guidelines how to determine precision or repeatability, there's hardly any in the I would say non-MS specific guidelines any information on that, simply because for determination of the repeatability, they suggest to use identical items, or more specifically in the Commission recommendation, they say you should use 80 electrovolts of a blank material, which means they do not consider that a maize sample from let's say Argentina might have exhibit different matrix effects compared to a maize sample from Europe. In contrast, in the field of bioanalysis, there has been already in 2003 a very heavily cited paper that observed differences in matrix effects for a specific drug in different lots of human plasma. And they came to the conclusion that you should check matrix effects in at least 5 different sources, and the slopes of the standard lines should be practically the same. And well, practically the same is a very inconvenient term when it comes to quantitative analysis. So the European Medicines Agency guide, they have specified this, and they recommend to analyze matrix effects in at least 6 lots. And it definitely advise to against pooling the matrix. And the coefficient of variation of this matrix factor calculated from the 6 lots should be not greater than 50%. And how does this, what's the situation in our method? So the data which I've just presented a couple of slides before is based on 7 different individual samples per matrix. And in order to challenge the system, we went for a maximum maximum diversity of the samples. So for example, for maize, we have included two varieties from Africa lacking the beta-carotene, and we have extracted and spiked the extracts and plotted the RSD of these 7 replicates of individual samples compared to 7 technical replicates of the pooled extract. As you can clearly see, the coefficient of variation in the 7 individual samples is much higher. And what we observed was a pattern that there were 2 clusters, sample number 5 and sample number 7 being different to the other 5 samples. And very interestingly, this does not correlate with the color. So sample number 4, which was one of the African samples, was belonging to one cluster, whereas sample number 7 was belonging to the other. And so we thought, okay, well, probably very probably this relative matrix effect is the variation of the absolute matrix effect within individual samples of a given matrix for sure significantly contribute to the method's uncertainty. And indeed, when we plot the repeatability of these 7 matrices, so here again, that's the pistachio samples. Also here, we had extracts ranging from brown to greenish, and this one was, I can't see it well on the screen, but it was rather purple. Again, that shows that we tried to include as much diversity as possible, and it was some 85 to 97%, which complies to the criteria for repeatability of those 20%. But you have to keep in mind this criteria is specified really for technical replicates from the same sample. And so we wonder if you sort of introduce this additional source of uncertainty by using different individual samples, whether or not it should be considered to expand this criterion for repeatability, for example, to 25%, which would be just following the law of error propagation based on this 20% criteria for technical replicates plus the 50% criteria for the relative matrix. That's for the repeatability. And what we also did was to determine the intermediate precision. And for this, we spiked technical replicates of just one of the individual samples. And we analyzed one of the 7 replicates each in a time interval of 7 weeks. And the European Committee for Normalization has established a criteria for this intermediate precision, which is 20 to 30%, depending on the analyte concentration. And as you can see, it's more than 96% of analytes complying to this criterion, so just that the red bar is outside. And what was interesting is to compare now this intermediate precision based on technical replicates from one sample compared to the repeatability deriving from 7 different samples. And indeed, for 60% of all analytes, this intermediate precision was smaller than the repeatability in the same sequence based on different samples. So, for example, aflatoxin B1 in maize was maybe most striking example. The intermediate precision was 6.5%, versus the 18.7% on the data in one sequence deriving from 7 different samples. So we concluded that the contribution of this relative matrix effects to the method's uncertainty is substantial and should be a top priority in validation process. And to try to quantify this contribution, we calculated the intra-laboratory measurement uncertainty on 2 ways. First of all, what we did in parallel is for maize and for figs, also to determine the repeatability of 7 technical replicates within one sequence, and compare this to the data that we have obtained on the repeatability data of the 7 different samples. And then the combined measurement uncertainty combined is, again, following the law of error propagation, is the square root of the uncertainty of the intermediate precision and plus the uncertainty of the apparent recovery for the single lot and for the lot per lot. And that's the result. So every blue dot we have just calculated this for some 60 compounds. So that's a paper from a PhD student. And every blue dot here represents one analyte, and red bar is the median. And the 40% is the green line is the maximum intra-laboratory combined uncertainty suggested by the European Commission. As you can see, if the compared uncertainty based on the single lot is significantly lower than the one which takes into consideration the relative matrix effect. So in figs, the median increases from 24 to 32%, and in maize from 22 to 32%. So we concluded here that this evaluation of this lot-to-lot variation, or the relative matrix effects, it estimates your uncertainty in a more realistic way. And I think that's really one gap that is missing in the regulation. This should be taken into consideration. However, when it comes to the workload, this means, of course, even more work when validating such a method. And the question is, well, is this really needed for every matrix? Well, that's a little bit difficult to answer. So maybe I can use this slide to persuade it. It can be well worth trying. So that's actually showing the compiled results of our method, of its performance in proficiency testing. So we're participating in a ring trial scheme organized by a French company, as it has quite a lot of different matrices included. And our performance is quite well. So we have at the moment a success rate of 95.4%, although we are one of the only few labs that do not include stable isotope labeled dilution for correction of matrix effect. And as you can see here, there's a lot of matrices for which we do not have any full validation data at hand, and for which we estimated the contribution of the matrix effects with a skilled guess. It works for most for most matrices, but you can see here and here two clusters of results, and this one was, if I remember correctly, licorice, and this one was green pepper, where actually the non-availability of full validation data led to an under or overestimation of the results. So the message is probably you should do it for each matrix. The question is, okay, then let's do it, but there's now the problem of how to manage the workload. So for the data I've shown you on the 7 matrices, I calculated how many chromatograms we're dealing with. So we had 5 concentration levels. We had 3 types of samples: the external standard spiked sample, spiked extract, 7 replicates per matrix, 540 analytes, 7 matrices times 2, because you have to check quantifier and qualifier chromatogram, which comes up to some 800,000 chromatograms, which, if it's at very low levels, you all have to manually inspect. And to be honest, for the data that derived from this study, I think both me and my PhD students, we worked, I think, some 2.5 years just on data evaluation. So that's probably nothing you want to do in routine, unless you have many PhD students. So what's the options to reduce these workloads? Well, there are several guidelines being aware of this problem. So the FDA guideline says that it becomes actually unfeasible to carry out matrix extension validation for each matrix. And they say more realistic is maybe that you choose just one matrix of a matrix group, define high sugar or high water or dry matrices. This is also suggested by some day guidelines. So they come up with a commodity group and tell you, okay, you should validate at least one matrix per matrix group. And there has been also a recent report from the Joint Research Center in Europe, including the European reference laboratories. They suggest pooling matrices. Well, we tried to challenge this suggestion. Actually, what we have done here is now that we did a pairwise t-testing of both the apparent recoveries in red and the recovery of the extraction of the 7 matrices that we have investigated. And what you can see here, the situation is not very good as considers the apparent recovery. So it's the majority of combinations, more than half or even two-thirds of analytes show significant differences in their apparent recovery. This considers the recovery of the extraction. It's a little bit better. So some combinations show very good agreement. So between wheat and maize, it's only 9%, 9.5%, which show a significantly different recovery of the extractions. However, what this table shows that actually the concept of representative commodity is not supported by our data. So I've given the data for almonds in both. You can see it considers almonds. The most similar matrix is wheat. And this is also the case for the recovery of the extraction step. Again, almonds and wheat agree best. So that makes no sense if you try to follow these commodity groups. And therefore, we think that redetermination of some basic validation figures is necessary for each new matrix. Okay, what could be the next option? Well, the next option could be you reduce the levels. And the question is, well, why should we analyze different concentration levels? Well, this has been outlined in by the European Commission. That's the problem is that somewhere in the system there could be a population of active sites, for example, on a cleanup column, which absorb your analytes, and the recovery at very low concentration might be close to zero because your analyte is almost quantitatively bound to these active sites. Whereas at higher concentrations, the recovery might be effectively complete. That's why the European Medicines Agency has two levels, suggests two levels, and this 2002-657 guide, they suggest three levels, which again, for 18 samples times 540 analytes would result in close to 10,000 chromatograms. And the problem is, if you're very near the limit of quantification, automatic peak integration is not reliable, and you really have to cure the data by hand and check all the chromatograms. That of course needs a lot of time. So what we tried is actually we investigated whether there's any significant difference both in matrix effects and extraction efficiency between different levels. And I've plotted the data here for the three different analytes. So let's go for aflatoxin P1. That's the matrix effects. You see that there's no difference between within a factor of 100 of concentration. Well, that's not very surprising, because if this would not be the case, the concept of matrix matched calibration would not be feasible. However, and that's maybe less expectable, also the recovery of the extraction stays constant over the concentration level. So that's for free nitropropionic acid, which is some 74 to 82% on these different levels. And if you compare the spiked samples to the solid standards, so we have extended this now to 4 orders of magnitude in the concentration, still those values are not significantly different. And we tested this with ANOVA, and we found for the 540 compounds, just 32 compounds in maize and 29 in figs, that one of those values was significantly different to the others. So the conclusion is, in order to determine your apparent recoveries and your extraction efficiency and the signal, the matrix effects, you can work at a very high concentration level. And the advantage is, at very high concentration level, the automatic peak integration is much more reliable, which means that you can just sort of copy paste the data from your data analysis program and further treat it in Excel or whatever you would like to. Okay, the idea of not analyzing very low concentration, of course, has one problem, which is the determination of the LOD and LOQ. Well, there has been a recent publication by a European reference laboratory pointing out that the LOD, LOQ for an LCM method does not exist, because compared to, like, let's say LCUV, the fluctuation of the sensitivity of the instrument is much higher than compared to LCUV, and so there are other sort of, and also depend on the method that is used for calculation. Very often the signal to noise ratio is used, but this has been discouraged recently by the European Reference Laboratory in a technical guideline, and also some MS transitions do not exhibit any noise, so there's no noise to divide, and you sort of do not get a meaningful number. There's the URLs, they suggest a calibration approach, so 5 levels in duplicate, with the highest levels should not exceed 10 times the estimated LOD. And there's some other approach based on blank samples, but that's for a multi-analyte method really, I would say, very impractical, because you would need to adjust the concentration of these 550 compounds in a way that in your final vial that you inject, that all of them are near to the LOD and the LQ. And for our method, I tried to come up with a calculation, okay, in which way I have to pipette those 550 compounds together that you really match to the level of the LQ, and that was absolutely impossible. So what we did for estimation of the LOD and LOQ, we determined it according to the Eurochem guideline, and this is based on the measurement of 7 replicates spiked at very low level, and the Eurochem guideline is rather conservative, so it considers that at the level of LOQ you should obtain an RSD of 10%. And the way of calculation is such that if at a certain concentration range you obtain an RSD of, let's say, 5%, the LOQ is exactly this level multiplied by 2, which is the bonus that you get for obtaining 5% instead of 10%. And what I've plotted here is actually a comparison of the LOD obtained in FIX and in MACE, and you see very good correlation. And what we found out that actually the numerical values of given analytes between the comparison between the LOD, LOQ in wheat, in maize and FIX, they differ by only a factor of 2, only for 10% of all analytes. So we think that the most pragmatic approach is to establish a general LOD, LOQ for each of your compounds using a very conservative approach as the Eurochem, and use it sort of in general until you have good reason to expect that for a particular matrix, due to an interference, the value will be worse. So that's actually shown here. So there are a couple of other compounds with other columns which actually sort of deviate from this correlation. So the pink ones are where we observe the elevated baseline or an interference on one of two matrices, which of course led to inferior value for the LOQ. So before I come to a general conclusion, I would like to get a few slides on the sort of the next level we are exploring. So we are interested whether all these conclusions we have drawn on mycotoxins in 7 raw commodities are true as well for extended scope of the method. So it's to the microbial metabolites, we've added some 500 pesticides, 160 veterinary drugs, plant toxins, unspecific metabolites, and also to challenge the system by going to complex feeds. And for this wide range of compounds, of course, the the mess in the chromatogram becomes even more severe. So in the positive mode, there's now more than 1,000 analytes included. When it comes to compound FINT, well, compound FINT, it's very important agricultural product. So in 2018, more than 1,000 billion tons of compound animal feed were produced, and the composition varies depending on the animal you want to feed. So for chicken and pigs, it's mainly a mixture of grains and soy, of maize, soy, and with some TDHs. But for cattle, it's more complex. So it's consisting of 80% green fodder, it's wheat, silage, hay, and 20% concentrated milk, maize cereal oil seed. So what we tried is to have some sort of pre-validation for all these raw ingredients, and the picture was for most analyte matrix combinations the same. So the recovery of the extraction here in green, that's aflatoxin B1 in the cattle feed ingredients, and in cattle feed is in the target range, whereas you have significant matrix effects, and of course then the apparent recovery is also quite low. And we were wondering how this repeatability looks like in a complex mixture where the fraction of the individual ingredients shows variation. So what we tried is we spiked 7 replicates from 7 real feed samples, and you see that, well, that the standard deviation for some of the compounds is really outside the target range of 0 to 20%. Partially because for many analytes, it's difficult to find really a blank sample. So we had to deal with the microheterogeneity of the material, that one sample might be different in its background concentration of a certain analyte than the next replicate, and that's actually why we think part of the values showing a higher RSD are explained. If you go to the way which is suggested by the guidelines, so you use certain technical replicates from just one real sample. On the other hand, I mean, the result looks nice, but most probably, again, as alluded earlier, you are going to underestimate your method's uncertainty, because here again the contribution of the matrix effects showing variation from one sample to the other are substantial. So what we tried to come up with, and this, if you're interested in that, I ask you to consult this paper of my former PhD student David Steiner, and we received the ACS Paper of the Year award for this, for which we are very proud of. We prepared model samples, you can see it here, prepared from true blank single ingredients, and we mixed together with a varying composition. And you see that actually the RSD is somewhere in between. It's still, most of the analytes are below 20%, but for sure this gives you a more realistic estimation of methods uncertainty. And that's actually what we suggest to do for compound feeds, that you try to model them based on a simple blank ingredients. So with this, just a quick look at the validation data. So upper part is cattle feed, lower part is chicken feed. As I've already said, extraction efficiency, green bar, and here the orange bar is in the target range for more than 90% of all compounds. But also the relative standard, whereas of course, as I said before, the matrix effects, and of course, as a consequence, also the apparent recovery are below 70% for a good fraction of the analytes. But it's also the repeatability, which we consider to be quite good. So as you see this criteria, some 96 to of all the compounds that we investigated were within the target range. And this is just to sort of show that the different compound classes here, so the bacterial metabolites, mycotoxins, pesticides, plant toxins, veterinary drugs, they all behave in a similar way. So there's no class of compounds which shows some dramatically different behaviors, considers matrix effect or extraction efficiency. When it comes to sensitivity, it's I would say the same, except maybe that's it considers the plant toxins. So there are several simple phenolic compounds which exhibited quite a high baseline. That's actually why those exhibit LODs and LLQs that are maybe a little bit worse than the other compound classes. But most MRLs that are set for food-based matrix are covered by our method. So with this, I want to come to my conclusions and to recommendations. And what I really, what's striking for me is that everyone involved in mass spectrometric analysis knows that matrix effects are a critical aspect. And there's really a discrepancy, I think, to the guidance in official documents, which is in my point, at least to a great part, lacking. And this already starts with differentiation between matrix effects and recovery. So in several guidelines, you cannot be completely sure what exactly this guideline refers to when it talks about recovery. I think that the relative matrix effects are probably more critical than absolute matrix effects, simply because they cannot be compensated by matrix match calibration. So they might be, as I said, they might be quite different in a mace sample from Argentina compared to the sample from, let's say, Europe that you use for matrix matching. That's why validation should, in our view, be performed replicates from different individual samples, so at least 5 in our view. And I think there's just the need to do at least, I would say, some evaluation whenever the matrix is to be transferred to a new matrix, when the method is to be transferred to a new matrix. Fortunately, there are some options to reduce the workload for a method covering so many compounds. So in our view, it's sufficient to investigate one concentration level, a high concentration level, which reduces the need of manual intervention for the peak integration. So at very high levels, you can trust the automatic integration. And I think we also think that there's no need to determine LOD and LOQ for each analyte for each new matrix, because we've seen that even between diverse matrices, the difference in the numerical value is low. So if you come up with a conservative estimation and the sensitivity of modern mass spectrometers is so good that any concentration below this conservative estimation of LOD and LOQ is, I would say, only of minor relevance anyway. I mean, if you do not consider banned compounds like banned antibiotics, I think this general approach is pragmatic to reduce the workload. So now the ultimate shortcut for a method transfer to a new matrix is to spike 7 individual samples at a high concentration level. This helps you to get the apparent recovery and to reveal if there's any specific interference or elevated baseline noise that might pose the need to have a look at low concentration to see whether it might be necessary to adjust the LOD, LOQ for exactly this analyte matrix combination. So with this, I would thank the European Union for funding a EU project where a large part of this work has been done. I thank my two former PhD students, David Steiner and David Stadler, who were busy with data evaluation a lot. So David Steiner, I think, spent the first lockdown in Austria 6 months just with data integration of the multi-class method, and Christoph Büschel, who did the statistic treatments. And I thank you for listening to me, and I'm happy to answer any questions if there are.
Thank you so much, Michael, for your excellent and clear presentation. And I'm sure there are many aspects that now we have to consider in order to work with the multi-toxin method that you were presenting to us today. Also, it's a challenging analytical task, and I think there are many points of view to consider, and in terms of matrix effect, it's a topic not exhaustively treated in papers and publications, so it's really interesting the view that you gave us today about how you in your lab with such many analytes you proceed in such diverse samples to reduce the workload, as you say before. Regarding to questions, I think I don't see many in the YouTube transmission. There are some consideration related how the validation guidelines of the FDA are different to the ones that you were talking about that you apply from the European Union. Do you have any consideration in those terms? And
well, what I like about the FDA guideline is that that they consider that validation data based on just technical replicate might actually underestimate your method uncertainty. So I think they have a sort of, they recommend to have different sources for your validation data, but they are more concerned about differences in extraction efficiency than matrix effect in particular. But I think it's better to be concerned, maybe because of a minor reason, than not being concerned at all. So if I remember correctly, it's like the FDA distinguishes between sort of a method that just emerges due to sort of some emergency, for example, like spillage of some pesticides somewhere, and the related authority has to come up with a method within maybe a few days to cope with this acute problem. And then they gradually increase to a fully intra-lab validation and to inter-lab validation. And with sort of the, how to say, increased scope of the method, they strongly recommend to use different sources of this particular matrix. And that's, I did not find anything in the European regulations at all, to be honest.
Okay, and here we have a comment of from Dr. Omar Amador. Well, thank you for your talk. And have you compared the recoveries using native versus isotopically labeled compounds? Are they similar?
This has not been included in this study, but a colleague of mine has elaborated on this some years ago. And as I said, no doubt, if you're focusing on the mycotoxins addressed by regulatory limit for each of them, stable isotope labeled standard is available. No doubt that's the gold standard. But it comes already to, you have already to consider where to add the internal standard. So if you add them just to the extract, for example, with an auto sample program, so that's something we have we have implemented in some other project that the internal standard is added automatically to the sample. We are just from auto sample a while with an auto sample program, which is just to minimize the consumption of this very expensive standard. I think the additional cost we calculated to be somewhere in the range of €2 per sample. This actually compensates, of course, for the matrix effects, but not for extraction efficiency. You can also, of course, compensate for extraction efficiency, but then you would need to add your standard already to the sample. And of course, you need quite a large amount for that. And I think this is not feasible simply from an economic point of view. And if I remember the work of it was actually Elisabeth Wager, one of our former PhD students. She really sort of she did this actually on an instrument that was even more prone to matrix effect than the one we use. And what she could show that actually matrix effects are effectively compensated, but of course any incomplete extraction still remains. And yeah, that's you have to deal with. And I think these internal standards are sort of the most, or the value is that they of course can also compensate for the relative matrix effect, because you add them to each of your individual samples. Whereas if you rely on matrix calibration, you have to rely just on one sample or pooled sample, which is at the end of the day the same. And you hope, or probably, or you should have taken into consideration during method validation, that actually the differences in matrix effects between, as I said, sample from Argentina to sample from Africa to sample of Europe with different varieties and maybe different agricultural practices do not exceed a certain percentage.
Thanks, Michael. And one last question. If people in the chat have more questions, they can send us to the email from the seminars, and we can translate those questions to you, Michael.
Yeah, I'm perfectly fine if anyone emails me directly. I'm also happy to answer.
Okay, thank you. And the last question is, how do you consider the concentrations that you use for spiking the samples? Since you have such many analytes, such many diverse samples, I was wondering if you take into account the maximum allowable limits of the regulation. How do you choose those concentrations?
Well, that's a good question. In this, if you just take the method on 900 metabolites alone, it's just maybe some it depends on what you consider with regulations. So, for example, they are ergot alkaloids. They have some recommendation, but not regulation. But okay, let's include them. You end from those 900 compounds with maybe some dozen of compounds for which there is any regulation. And I would say the problem is that the relevant concentration do not correlate very well with actually the LCMS sensitivity. So if you pipette together your compounds like aflatoxin, ochratoxin A, and deoxynivalenol, and to match them on the same concentration, you will get quite a, I would say, diverse signal. If you ask me what's the spiking level, well, the highest spiking level, I think we did it in a way that for aflatoxin and ochratoxin A, it's in the range of regulations, which means it's somewhere in the region of 10 micrograms per kilogram. Of course, if you consider baby food, that's at least one order of magnitude lower, but for raw commodities, I think that's a reasonable value. Whereas for SAEM toxins like deoxynivalenol and the formolacins, we are slightly below. So it's something like for the formolacins, I think we spike at 1 milligram per kilogram, and for DON, it must be something like 500 microgram per kilogram. But that's, I would say, it's historically grown. Yeah, so we start with some 40 compounds, and then every 1 or 2 years we add some new, and we keep all the compounds in intermediate mixtures of combining 10 compounds, and we are not completely free anymore. How to say, to reshuffle the concentrations. And simply because as I said, I tried it once to do it in a way that all the compounds are near their LOQ in a certain dilution, but I failed. With the number of compounds being too high, that's becoming impossible.
Okay, Michael, thank you so much. Well, to finish this meeting, again, we truly appreciate the time and effort you took to share your thoughts and experiences with us. And many, many thanks for being with us today. Also, many thanks to the audience, and we hope to see you all in our next seminar, which, if you allow me, I will stop your presentation.
Okay.
And I will share a little bit slide for our next talk. Here we have. Okay, first of all, well, once again, I think all are familiar now that we have a cycle of 6 seminars, and thank you, Michael, for being the first one in these talks, and thank you for your excellent presentation. Our next talk is from Dr. Susan Abatiello, and is about proteomics related topics. We have here the name of the title of the presentation, and it's going to be next Thursday at 5 p.m. Argentinian time, and the way to register is the same that we had for the Michael talk. So we will be promoting all this information in our website and in the social media. And of course, as Ricardo said before, and we also take advantage of this opportunity to invite all of you next year to the 4th Congreso Argentino de Espectrometría de Masas. So thank you all for being here today. Thank you to the audience, and of course, the institution who help us carry out with these seminars: Universidad Nacional de San Luis, Facultad de Química, Bioquímica y Farmacia, CONICET, and the different empresas who support or will support these talks: Analytical Technologies, D'Amico Sistemas, Genk, and Soluciones Analíticas. Thank you so much for being here today, and we hope to see you all next week.
Bye-bye.
Thank you, Michael. Thank you so much.